So good morning together. Today I want to talk about the solution of the telegraph equation. Our starting point is the equivalent circuit of a transmission line section. This section is given between the coordinate z and z plus delta z. The inductance accounts for the magnetic field stored in this section. The capacitor accounts for the electric field energy, which is stored in this section, and the series resistance account for the losses due to the current, and the conductance account for the losses due to the voltage. And in this limit, we know delta z tending to 0, we get this differential equation, which is a second-order linear homogeneous differential equation with constant coefficient. And to solve this, we will talk with a mathematician, and he will tell us, try the exponential function. And so we, as a trail function, we use the function u of z is u naught times the exponential function of minus gamma z, where gamma is a constant we had to introduce. And if we choose gamma to be equal to this value, then this equation will solve the differential equation, and this constant is called complex propagation constant. And for the current, we will get this equation, so E of z is proportional to the derivation of u of z, and if you calculate the whole equation, then you end up in this equation, which we will consider later in more detail. So in principle, we got the mathematical solution now. We have this differential equation, and this differential equation is solved with this exponential function, where we have to choose gamma, but since we have a square root here, we have a plus or minus this value. But as you see, these are all very complicated expressions. In principle, we found a mathematical solution, but what does this mean for an electrical engineer? It's not quite clear at the moment, so we will reduce the problem and we have a look to a lossless transmission line. So in the case of the lossless transmission line, R prime and G prime will be 0. So this will reduce, of course, then our constant gamma, and gamma will go over in J beta, with beta must be chosen to be equal to omega square root of L prime C prime, which is called phase propagation constant, because you see in this equation the voltage u of z will only be changed in the phase along the transmission line, while its absolute value remains the same. And also in the next step, of course, this is a quite complicated function in the complex plane. So what we want to do now is we want to convert this function into a real function of space and time, and this can be done with the help of this equation. So we end up in this equation, which is a function of space and time. It's a sinus function omega t minus beta z. But what does this again mean now? For this purpose, I sketched here this function at two different time points. Sorry, I have to go back. Two different time points. One is at the time t equal to 0. This is the blue line here. This is the blue line here. And one for the time t equal to a certain point delta t. And of course here we have a sinus function, and I call this the total phase. And now I want to have a look to this total phase, but to a special point of the total phase, which I call phi equal to 0, and this is in principle this point. And the question is now, what happens with this point if we change the time? So you see, I can see now this point will propagate in the positive z direction, and this seems to be this is a this is a velocity, and this velocity is called the so-called phase velocity. So this function now describes a wave propagating in the positive z direction with this phase velocity. And if I calculate, for example, now, or have a look to the distance between this point and the point where the function repeats, so we can define now the wavelength, and this wavelength is given by 2 pi over beta, which is equal to the phase velocity divided by the frequency of the exciting wave. And now we can summarize this a little bit, and we can see if I have a function, exponential function minus j beta z, this describes a wave traveling in a positive z direction. Of course, we have to account for two different signs. So if I have a look to the function exponential function plus j beta z, this describes a wave traveling in the negative z direction. And now we can write for the voltage and current distribution of a wave traveling in the z direction. We can say this is u of z is u naught, this is a constant, exponent minus beta z, and I of z will be equal to u of z divided by zc, where zc is given by this equation, which is the so-called characteristic impedance of the transmission line. Since the characteristic impedance of the transmission line has a real value, there is no phase change between the voltage wave and the current wave. So we can say if I have a single wave on a lossless transmission line, the voltage wave and the current wave are in phase. To go on in our discussion, we now have a look and compare our transmission line theory to Maxwell's TEM waves. If we come from the transmission line theory, we have this phase velocity, which is given by 1 over the square root L over C. So according to the transmission line theory, it seems that L prime and C prime can be changed independent of each other. But if you start with Maxwell's theory, then you will find that in the Maxwell theory, the corresponding waves, which are called the TEM waves, they have a phase velocity which is C naught divided by the square root of epsilon r if the transmission line is embedded in a certain dielectric, while C naught is the speed of light. So what we can say, according to Maxwell's theory, L prime and C prime are not independent of each other, and if you go into the TEM waves, the reason will be because the electric field and the magnetic field lines will always be perpendicular to each other. To calculate the wavelengths on a transmission line, we will instead use now the following equation. Lambda is of course the phase velocity divided by the frequency, And this is then C naught over the square root epsilon r divided by f. So this is the equation we will use to calculate the wavelengths on a transmission line, where we have to know, of course, the relative permittivity where the transmission line is embedded. So now we come to the point where we will discuss the transmission line with low losses. So in the RF range, where the following equations normally hold true, that R prime is much smaller than omega L prime and G prime is much smaller than omega C prime. And this yields for gamma in the first approximation to this equation here, which can be separated in alpha plus J beta. And in the case, also in the case of the transmission line with low losses, we end up in the same equation for beta. It's just 2 pi over lambda. But now we have to introduce a further constant, which we call alpha, and this is the so-called attenuation constant. And the equation is given like this. It's R prime divided over 2 ZC plus G prime times ZC. But the point now is R prime and G prime are normally functions of the frequency, so it's not easy to calculate the attenuation which a wave on the transmission line undergoes. So as a summary, we can now find for the solution of the transmission line with low losses, we have the wave here traveling in the positive z direction, but now this wave is attenuated by this factor, while the current wave will be in phase with the voltage wave because of the real value of our characteristic impedance. The beta is already defined like this, and alpha like this. These are the values which also hold true in a lossless case. But if there are losses present, we have to account for alpha, which accounts for the losses. But a very important point is that also for a transmission line with low losses, we will have a characteristic impedance which shows a real value, and this is true for the RF range and also for the microwave range.